Hello students, welcome back to our class. We shall be discussing some more examples of subrings in today's lecture. So let us have a look. The first one is show that the set twice z equal to twice n such that n belongs to natural number is a subring of z under usual addition and multiplication of integers. Okay. So we need to show that the set twice z, that means the set of multiples of 2, okay, is a subring of z. Okay, so first of all I have to show that it's non-empty. So the most obvious element which is there in this set is 0, because 0 can be written as 2 into 0. Okay, any element that can be written as 2 into some integer is there in the set twice z. Okay, in particular 0 can be written as 2 into 0, so it is there in this set twice z. Okay, so 0 is a member of twice z and hence twice z is non-empty. So twice z is a non-empty subset, so that's fine. Now we will take any two elements from twice z and we will show that their difference is in twice z as well as their product is also in twice z. Okay, so let a comma b belongs to twice z be any element, then a will look like 2 into some integer, okay, and b will also look like 2 into some other integer n. Okay, so I have written a equal to twice n, twice m and b equal to twice n for some m comma n inside integers. Okay, so what is a minus b? A minus b can be written as twice m minus twice n, which is twice m minus n, but z is already a ring, so m minus n is an integer, right? So a minus b is an element in twice z. Okay, because a minus b is written as 2 into some integer. Okay, so whenever anything is written as 2 into some integer, it is there in the set twice z. Okay, then what is a dot b? The product is twice m into twice n. This can be written as 2 into twice mn, but twice mn is also an integer, so it's the product is in twice z, hence twice z is a subring of z. So we had done the subring test. A non-empty subset is a subring if it is closed under subtraction and multiplication. Okay, so this is the thing that I have used. So let us generalize this for any integer a inside z. The set az equal to the multiples of a. Okay, so that is a n such that n belongs to z is a subring of z under usual addition and multiplication. Okay, the proof is exactly similar. We have 0 can be written as 0 a into 0, so 0 is an element in az, so az is non-empty, right? And if we take any xy inside az, so here you observe that I have not taken ab because already the symbol a is given in the question. Okay, so we cannot mix up the symbols, right? So I have started with xy, any elements xy in az. So x can be written as a into some integer, y can be written as a into some other integer, right? So what is x minus y? X minus y is am minus an, which is a into m minus n, which belongs to az, right? And xy can be written as am into an, and this is a into amn, right? And which again belongs to az. That means we have shown that x minus y and xy belongs to az whenever x and y belongs to az. So az is a subring of z. Okay, so the proof is very similar. So instead of az, if in your exams it is asked that show that 3z is a subring of z, 5z is a subring of z, the proof is exactly similar. Okay, so one thing we have to note is this: the subrings az of z with a not equal to plus minus 1 do not have the unity, that is 1. Okay, the element 1 is not there in az because 1 can be written only as 1 into 1 or minus 1 into minus 1. Okay, I cannot write 1 as 2 into something. I can write 2 into half, but half is not an integer, right? So in the set of integers we cannot write 1 as anything else, any other multiple of any other number. Okay, that cannot be written. So that means az does not have unity. Whenever a not equal to plus minus 1, az doesn't have unity. Okay, so yeah, so one thing that I had remarked in the earlier class, we had shown that the intersection of any two subrings is also a subring, but I had remarked that the union, the same thing is not true for union, that is union of two subrings may not be subring. So this is one example we can show the union of two subrings may not be a subring. So for example, twice z and 3z, okay, they are subrings of z. Just now we have proved, but twice z union 3z, it is not a subring. Okay, why it is not a subring? Because it is not closed under addition. You take two elements, so 2 and 3 are elements inside twice z and 3z, because 2 can be written as 2 into 1, 3 can be written as 3 into 1, so 2 and 3 are elements inside twice z union 3z. But 2 plus 3, which is 5, which is neither a multiple of 2 nor a multiple of 3, so twice z union 3z is not closed under multiplication. Okay, that is the sum of 2 and 3 is 5, which is not there in the set. Okay, even we can show it the other way. The difference of 3 and 2 or 2 and 3, difference of 3 and 2 is 3 minus 2 is 1, which is not there inside twice z union 3z. Okay, so union of two subrings may not be a subring. Okay, another problem, let us take up. Let R be a ring and A belongs to R, be any element. Show that the set X belongs to R such that AX equal to 0. Okay, all those X inside R which satisfy that the product with A is 0. Okay, is a subring of R. Okay, so we have the element 0 is in R and 0 also satisfies this. A into 0 is 0, right? So 0 is in S. Okay, by definition of the set S, 0 is in S. So S is not equal to 5. Okay, S is a non-empty set. So next I start with any two elements inside S. So let us take it as x comma y inside S. Then by definition AX is 0 and AY is also 0. So what is A into x minus y? It is AX minus AY, but AX is already 0. So and AY is also 0. So 0 minus 0 is 0, right? So A into x minus y also is equal to 0. So that means x minus y is an element of S. Okay. Similarly, A into xy can be written as AX into y, and AX is already 0. So 0 into y is 0, and therefore xy is an element in S. So what I have shown that x minus y and xy belongs to S whenever xy is in S. That means S is a subring of R. Okay. Next, another example. Let z root 2 equal to a plus b root 2 such that a b belongs to integers. That means z root 2 is the collection of all those real numbers which are of the form a plus b root 2, where a and b are integers. Okay. So prove that z root 2 is a ring under ordinary addition and multiplication of real numbers. Okay, or the question may come this way also. Z root 2 is a subring of R with respect to addition and multiplication. Okay. So first of all, we show that it's the 0 element is in z root 2. So 0 can be written as 0 plus 0 root 2. So it's there in z root 2. So z root 2 is not a empty set. Okay, it's non-empty. Next, I start with any two elements inside z root 2. That those two elements will look like a plus b root 2 and c plus d root 2 for some a b c d inside z. So x minus y will be a plus b root 2 minus c plus d root 2, which can be written as a minus c plus b minus d into root 2. Okay, but a minus c and b minus d are integers. So this particular expression, it will also belong to z root 2. Okay, and then you calculate what is the xy. Xy is a plus b root 2 multiplied with c plus d root 2, and if you just make a quick computation, it's ac plus twice bd plus AD plus BC into root 2. So AC plus twice BD is an integer, AD plus BC is an integer. So it's of the form some integer plus some integer into root 2. So it's an element inside Z root 2. So we have shown that x minus y and xy, they belong to Z root 2 for every xy inside Z root 2. So we can conclude that Z root 2 is a subring of R. That is, Z root 2 is a subring of the ring of real numbers with respect to usual and addition and multiplication. So if your question is show that it's a ring, then you can just write this additional line. Hence Z root 2 is the ring itself. Okay, we have shown that it's a subring of the set of real numbers, so it is itself a ring. Okay, next let us take up another problem. Let R be a ring. Prove that a square minus b square is a plus b into a minus b for all a b in R, if and only if R is commutative. Okay, so the famous formula of a square minus b square, it doesn't hold this way in all rings. Okay, it holds only when the ring is commutative, that is AB equal to BA. Okay, otherwise it's not true. So let a square, so there are two parts here, if and only if. First I have to assume that a square minus b square equal to a plus b into a minus b for every ab in R. Okay, assuming this, I have to show that R is commutative, and the other way, I have to assume that R is commutative, and then I have to show a square minus b square is a plus b into a minus b. Okay, so first let us assume that a square minus b square is a plus b into a minus b for every ab in R. Okay, and then we just split the right hand side using the distributive law. So it's a into a minus b plus b into a minus b, and then you can write this one as a into a minus a into b. So all these are distributive property. Okay, and a into a can be written as a square minus this is ab plus ba minus b square. Okay, so ultimately I have got the a square here will get cancelled with a square here, because in a ring the cancellation laws hold. Okay, and minus b square here will get cancelled with minus b square here, because in a ring the cancellation laws hold. Okay, so this is what I have written by cancellation laws in R. That means ultimately I have got minus ab plus ba is equal to 0 for all ab inside R. Again, by adding ab on both sides, you can show ab is equal to ba for all ab inside R. That means R is commutative. Okay, so it's very important to write, to keep on writing this particular line here for all ab inside R. Okay, because if we want to show that R is commutative, this equation should hold, or this relation should hold for every ab inside R. Okay, so that's why this line is important. Conversely, let R be commutative, then ab equal to ba for all ab inside R. Right. Next, so let us. So what I have to show? I have to show that a plus b into a minus b is a square minus b square. Okay, so let us write for all ab inside R we have a plus b into a minus b is just apply distributive law as before. So it's a square minus ab plus ba minus b square. So a square minus ab plus ba minus b square, so equal to a square minus b square, because ab and b are equal. Okay, by this one equation 1, ab and b are equal. So I can replace ba by ab, and ab minus ab is always 0. Okay, so a square minus b square is a plus b into a minus b for all ab inside R. So whenever R is commutative, this property is satisfied. Next, another problem. Suppose that R is a ring and a square equal to a for every a inside R. Show that R is commutative. Okay, so this ring is called a Boolean ring. Okay, any ring which satisfies this criterion, it's called a Boolean ring. It's named after the famous mathematician who was also the father of modern computers, George Boole. Okay, so it's a ring which satisfies this property, a square equal to a for all a inside R is called a Boolean ring. Okay, so if it's a Boolean ring, we have to show that it's commutative. Every Boolean ring is commutative. So let AB belongs to R be any element. We have to show that AB is equal to BA. So since AB belongs to R, so A plus B is also in R, because the set R is a ring. So by given condition, A plus B whole square is same as A plus B whole square, because A square equal to A square, A for all A, right? So just split it as per the distributive property. So we will get A square plus AB plus BA plus B square equal to A plus B. But A square can be replaced by A, and B square can be replaced by B. So we have A plus AB plus BA plus B equal to A plus B. Then we can apply the cancellation law. A and B will get cancelled from both sides. You will be left with AB plus BA equal to 0. But what do I need? I need AB equal to BA. Till now I have got AB equal to minus BA. So that is not working. So what we can do is we can just again multiply both sides by the equal quantities. So AB into AB will be same as minus BA into minus BA. Okay, but already we have done some properties of ring, that minus A into minus B is same as AB. Okay, so minus BA into minus BA is same as BA into BA, but BA into BA is again the notation for a BA whole square. Okay, but AB whole square is what? AB, because the ring is a Boolean ring. BA whole square is also BA. So ultimately I can write AB equal to BA. That means we have got AB equal to BA for every AB inside R. We started with any arbitrary element. Okay, so it's satisfied for any arbitrary element. That means R is commutative. Okay, another problem, let R be a ring with the property that A square equal to A for every A inside R. Then show that A plus A equal to 0. Okay, A plus A equal to 0 for every A inside R. So we start with any given element, any arbitrary element, then a plus a is in R. So what is a plus a whole square? It's equal to a plus a. So then I apply distributive law. So ultimately you will get a square plus a square plus a square plus a square equal to a plus a. But each of these a square can be replaced by a. Okay. So we have a plus a plus a plus a equal to a plus a. So by cancellation law, we again get a plus a equal to 0. Okay. So in a Boolean ring, the sum of any two elements is always 0. Right. So these are some of the problems related to subrings and rings. Okay, in the very next lecture we will be starting with integral domain. Okay, the concept of zero divisors, integral domain, divisibility. Okay, those things. So till then, thank you.